start with some simple stuff. This lecture is being captured and will be available on Vision as well. Yeah, you can see it, good. Okay, so before going into the details of this, I want to start off from a motivating example, which is the Tower of Hanoi. Do you know this? People? Yep. So I don't know about you, but I played with this when I was a kid. And in case you haven't seen it, let's have I'll just click Wikipedia. This is the Tower of Hanoi. So you get 3 sticks, and you get discs with holes in. And you put the game is to transfer all the discs from the left peg to the right. But the rule is you can only move 1 disc at a time, and you can only put smaller discs on top of bigger discs. Okay? I'll just go back to this and I'll write that down. So you've got a puzzle. You've got 3 discs, 3 sticks. And on these sticks, you've got these discs. And this is the starting position. And this is 1, 2, and 3. So we've got 3 pegs. And we've got n discs. And the disc is, has a hole in the middle. And they're different sizes. And the rule is you can move 1 disc at a time. And you can only put smaller discs on top of bigger discs. And the task is to move all the discs from peg 1 to peg 3. So using these rules to move all the discs from peg 1 to peg 3. Moving only 1 disc at a time and putting smaller discs on top of bigger discs. So let's think about numbers of discs. Okay, so we want to know the minimum number. The question is, what is the minimum number of moves we can do this? So what is the minimum number of moves? So let's look at n is 1. So 1 disc. So what's the answer for 1 disc? 1. 2 discs? 2? Yeah, because we can move 2. 1. Yeah, 2. Yeah. No, it's 3. Right? Because we have to take the smaller disc. We can't put it on 2, so we got it on 2. Then we put the bigger disc on 3, and then we move the smaller disc from 2 to 3. So we get, it's 3. Three discs. So now it takes a little bit more thought. I'm going to plop a few of these to stop me doing it later on. And I'll get that. So 3 discs. Let's think about it. So let's label these discs A, B, and C. So let's label the following. So we start off with, we've got the big one is A, B, C. And we've got 1, 2, and 3. So this is commonly the one you get in kids' games. or you get 4 or 5 if it's a nasty game. So what can we do? Well, we can move A. Well, here's A solution. We move A to 3. Okay. So then B can only go to 2 because. And then we're going to move A again, and we're now going to move A from 3 to 2. And now what we've got the discs in the right order on peg 2. Okay, so if we pause at that point, we've ended up with this. To get. So we've moved 2 discs, so we've taken those 3 moves that we did before, but now we've used those 3 moves to move it to peg 2. And now we move, the big one to peg 3, and then we do the 2 disc moves again. Right? So now we move A to 3, and then we do all the stuff on B, so we move the little one. Sorry, I've labeled them. The big one is C, the remaining one to 3, and then remember this one was A and this one was B, so then it goes A to, that needs to go to 1, B to 3, and A to 3. So we're just doing the 2 pegs shifts, but after having moved C to 3. So that takes 7 moves. But having done it in this way, you can kind of see there's a natural algorithm. So that links the number of moves for n to the number of moves for n minus 1. So what I did was I did the n minus 1 moves, then I moved the remaining disk, and then I did the n minus 1 moves again. Right? So this algorithm that you can kind of figure out from doing this is called the Hanoi recursive algorithm. So we can use the Hanoi. I'll tell you why it's called Hanoi in a minute. Recursive algorithm. And the point of this, it reduces the problem for n disks to the problem for n minus 1 disks. And that's the sort of essence of a recursive algorithm to the problem for n minus 1 disks. How do you spell disks? Is it K-L-C? Hmm? You also said it was C, didn't you? If you talk about... So if I talk about a compact, I'm kind of confused, because if you talk about hard disk, isn't it K? But if you look it up, and then, I don't know, I think there are 2 spellings, I don't know which is useful. I'm using K. I just noticed in the notes that Anatoly gave me, it said C, and that actually looks better. Anyway, so schematically, what do we got? We've got, so we split the problem up. We've got our column 3 disks here. Okay, so what we've got is we separate off, this is 1, 2, and 3 here. We separate off the biggest disk. So this is the largest disk. And this is n minus 1 disks on top, okay, this triangle. And then we move, we consider the algorithm to move the n minus 1 disks to 2. That says 0, that's because I got it on the wrong setting. Should be 3. So then the number of, okay, so let an, So what I'm doing now is I'm going to move the n minus 1 disks to 2. And that's going to take the number for n minus 1, because it doesn't matter, 2 and 3, it's just the labeling of the poles. So we move first to the following situation. Aha, I can do this. I can, oh no, I can't, because I've got that on the bottom. Okay, ignore me. I was going to cut and paste, I've got too much information there. Okay, so I've taken those n minus 1 disks and I've moved them to pole 2. And then you can see what I need to do now. I need to move the remaining disk to pole 3 and then move back triangular disks to pole 3. Okay. Then now you can't. It's coming. Come on, you can do it. We go. This is a really long way of. So I've taken this and I've moved into this now. Okay, so this is 1, 2, 3. Okay, I've missed this. There's a missing stage in here, so I go to this first, right? So I move this to this to this. And then I go to this. Right? So I moved the big one on 1 to the final one, and then I go back to that. So those are the steps I do. So as I've said, this is a recursive algorithm. And by linking, so let's let an denote the minimum number of moves. For n disks. Then what this problem does is it tells me the number an is equal to, well, let's think about it. In the first step, I have to do an minus 1 to move, I can point. To turn this into this, I need to do an minus 1. Then I do 1 extra, and then I do an minus 1 again. So from the above, we have the recursion relation that an is equal to 2 an minus 1 plus 1. Okay, so this recursive algorithm that links the n-disk problem to the n minus 1 disk problem turns into this relation between the numbers, which is a recursion relation. So this is an example. You get it? Anybody not get it? Question? So try it yourself. You've got one of these toys, or make one if you haven't. So For looking at the so that's the relation. You know, we want to know the answer. So we want to solve this recursion relation. That's what we're going to come on and do. But before that, so why is this called the Tower of Hanoi? It's because it was actually created, you know, by a mathematician. This puzzle this puzzle was written down in this form in 1883 by Edouard Lucas. But then immediately, probably because he helped it along, lots of myths were created surrounding this, that this was actually an ancient puzzle that had come from various places. So one of them, idea was it was Brahmin priests who had this temple in India with 3 worn out, you know, columns and 64 golden discs. And the monks took it in turn to move 1 disc at a time. And the question was, you know, how long would this take? It was this meditative exercise, and we'll come on to the answer in a minute, okay, to that. So that wasn't Hanoi, and that was another myth that, you know, there was a temple in Hanoi where the same thing went on. So 64 gold discs. So the question is, you know, how long for monks to move, or priests to move? Complete the meditative task. That's another animation. This is, of course, you know, it's just Wikipedia, right? But so, oop, what's that? Here we are. This is 6 discs, and it's using this algorithm. It's at a certain point, it will get to the point where it moves. See, it's sort of quite contemplative. There, that's the halfway through point, where you've moved them all to the middle. And then you do the same again. But you know, we'll be here all day, so we're getting there. Okay, done. So this claim is the solution is the following: that an is equal to 2 to the n minus 1. So for 64 disks, that will be 2 to the 64 minus 1. So suppose the monks moved 1 disk every minute. I'll leave it up to you to figure out how long this will take. It's a lot longer than the length of life of the universe. Okay. So this meditative task is not going to run out. Okay, so when such an explicit formula exists, we call it the solution of the recursion relation. So when such a, and I'll convince you it's a solution, and then we'll come up with general techniques. Explicit, such an explicit solution exists. We call it a solution of the recursion relation. And I don't want to keep writing recurrence relation, so I'm going to write R from now on, recurrence relation. But for now, let's just check it's a solution. And to check it's a solution, you bung it into the equation and check the left-hand side is equal to the right-hand side. Okay, so we take this in. So let's think about an. Well, an is equal to, or actually let's think about 2, the right-hand side of the equation. So let's think about 2an minus 1 plus 1. So let's check. That's the solution. So this is 2 to the 2n minus 1 minus 1. Sorry, I got the... yes, fine. So that's where we're plugging into the recursion relation. So this is this. And then we get plus 1. Okay. And now we expect that this is equal to an, so let's reorganize this. So this is just 2 to the n minus 1 times 1 minus 2 plus 1, which is indeed 2 to the n minus 1, which is an. So this does indeed satisfy the recursion relation. So this is a solution. This an is 2 to the n minus 1 is indeed a solution. Check. So more generally, the number of steps in a recursive algorithm satisfies a recursion relation, and we're interested in finding the solutions. Okay, so more generally, the number of steps in a recursive algorithm satisfies a recursion relation, and we're interested in finding the solution. Which is an explicit form for an. So before we go on to solving general things, let's look at another example. So recurrence relations often arise in counting problems. And counting problems are called, in mathematics, combinatorics. Okay? So combinatorics is counting problems, and it's a big branch of mathematics. So recurrence relations, so RRs, often occur in counting problems. Which are that is combinatorics problems in mathematics. So combinatorics, which is the fancy way of saying counting problems. So let's look at this example. So now we've got an example about climbing steps. We've got n steps. So here are our steps. And these steps, we can take them one step at a time or two steps at a time. Okay? So we can make either a single or double step in climbing them. So the question is, in how many ways can you climb a staircase? Right? Seems like and you'll have to mix single and double steps, right? And when you're given a problem like that for n steps, it's hard. But the way to deal with this is to go through small examples. And you look at 1 step, 2 steps, 3 steps. And by doing that, you get some numbers, but you also work out what the recursive algorithm is. Okay, so let's have n is 1. And let's call this an. We're calling this an. So what's a1? Yeah, when I ask a question, the answer is always 1. It's either 1, 0, or infinity in most questions. A is 2. That was a rare exception. And the answer wasn't 1. So imagine, I mean, you can try it out. You've got some steps next to you if you want. So how many ways can you climb in 2 steps? Oh, right, 2, yeah? You can either take 1 step at a time or 2 steps at a time, right? So, A3. Quite so obvious, but you can try it out if you want. Three, yeah. At which point it looks like there's a pattern, but that's often deceptive. Okay, there are many sequences that go 1, 2, 3, and then they don't go 4. And this is an example of one. Okay, because it's 3, because I can either do 3 single steps, I can do 2 steps on the first one and then a single step, or I can do a first step and then a double step. Right? So I can do 3 singles, 1 single, 1 double, or 1 double, or I can do 1 double followed by 1 single. So for 3 it's kind of easy, but for 72, it's not so easy, right? Or even 4 takes a little bit of thought. But there's a recursion relation. So, how do we think about this? I mean, so thinking about combinatorics problems is also just often a question about sort of thinking in the right way. And the right way in this case is to think about the last step, right? So the last step can either be a single or a double. What else can it be? So that's going to tell us the recursion relation. So if it's a single step, I want to write this in terms of some other an. So what is it? I mean the total number. So if I insist the last, what? N plus 1? No, keep going. I think you're on the right track, but So if I insist the last one is a single step, it reduces the problem to the n-1 case, right? So it becomes n-1. That's, I think, what you were attempting to say. So this is if the last is single, or the last can be a double step, in which case it's, yeah, an-2. So the last is a double. So it reduces what looks like a really quite complex problem into a very simple recursion relation. So this is a recursion relation that you've seen before. What is this? Anybody? So it's a sequence where the element of the sequence is the sum of the previous two elements of the sequence. Fibonacci, right? Yeah. So it's the recursion relation for the Fibonacci sequence, which certainly doesn't go 1, 2, 3, 4. So, and in fact, the same as the one for the Fibonacci sequence. Which has solutions 1, 2, 3, 5. I'm just summing the last two, 8, 13, 21. You get the idea. And comes up in all sorts of applications, including stair climbing, it seems. Well, this has an explicit solution, and we'll come on to that later. But first of all, I want to do some other recursion relations that you have met before, which including in school. Okay, so see you later for the solution. Okay, so let's do some other examples. And this is from school, really. So what we're going to do is we're going to do arithmetic and geometric sequences. So number one is arithmetic sequences. And the recursion relation, and then think about the solution. So the recursion relation for an arithmetic sequence is that, well, we always add some number to get the next number, right? So an is an-1 plus some d, where d is some fixed number. And you know the solution to this. The solution is the following. So the solution is, or if you don't know it, it's really easy to work out. So an, well, you've added, by the time you get to an, you've added d lots of n lots of d, so you get dn, d times n, and then it's plus some constant that depends on where you started. Where c is a constant that can be fixed by initial conditions. So just to see how that works in practice, let's do a simple example. Putting up a few more. E.g., solve the recurrence relation, a n is a n minus 1 plus 7, given the initial condition that a1 is equal to 3. Okay? Well, up there we wrote down the general solution, and I'm going to call it the general solution. So the language is really similar to differential equations. You have general solutions and then you have solutions. General solutions involve constants, which are fixed by initial conditions. Okay? So we'll make that a bit more formal in a minute. But so here we have that d is 7 in the above. So a n is equal to 7d plus c. No, d. 7n plus c. And then we stick in the initial conditions to define c. We substitute n is equal to 1 and use the initial condition that a1 is equal to 3. So that tells us, i.e., if we do that, we get that a1 is equal to 3, and from the formula we know that that's equal to 7 plus c. So c is equal to minus 4. And the solution is an is equal to 7n minus 4. Okay, and as I said just before, the general solution, the solution, or the general, don't know what else to call it, the general solution is called the general solution, I'm going to say. The general form of the solution that an is equal to dn plus c is called the general solution. To the recursion relation. Of the recursion relation. So the next one to do is geometric sequences. Okay. So that was arithmetic sequences. So let's do geometric sequences. So we want to write down the recursion relation. So the recursion relation is, so now we just multiply by something each time. So an is equal to r times an minus 1. And you know, whether we choose the initial n to be 0 or 1, it's kind of up to us. So I'm going to choose in this formula, I'm going to choose that this is n is 1, 2, 3. So that means I have a0 included, because it tells me that a1 is equal to r a0. So the sequence but I could choose it some other way. Sequence is A0, A1, A2, etc. So I decide to start from 0, but it doesn't make any difference. Well, let's look at what this sequence generates. So this sequence generates, this recursion relation generates the sequence, which is the geometric sequence. Well, it starts with A naught, and then we get R A naught, R squared, A naught, R cubed, A naught, dot, 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 it's infinite. And so we can just read off the general solution. So the general solution is AN is some constant times Rn. Okay? And by setting n is equal to 0, we see that that constant is just going to be the initial value of A naught. So setting the general solution looks like this. N is equal to 0. We see, in our case, that A naught is equal to C. So A naught is the initial condition, and that fixes the constant in the general solution, just like a differential equation. Anybody got any questions? Okay, so another quick example. Just to make sure we all know what we're talking about. Solve the recurrence relation AN is 2AN minus 1 with the initial condition A naught is equal to 5. And the solution? Well, here the multiplicative constant R is 2 in the general form I had. So here R is equal to 2, and the general solution is that AN is 2 to the n times C, where at the moment C is an arbitrary constant, that's the general solution, but then we plug in the initial conditions and we work out what C is. To find C, we substitute n is 0 and use into the general solution and use that A naught is equal to 5. So we have that, well, A naught is equal to 5, and that's equal to 2 to the 0 times C. So C is 5. And AN is therefore 5 times 2 to the n. Actually, this is a very natural place for me to stop. There's a slightly different section, so I think I'm going to stop here. And then so the next part is you start to talk about types of linear recursion relations, and this is for differential equations. You have linear equations, homogeneous equations, inhomogeneous equations, and you look at numbers of arbitrary constants and different order recursion relations, and those are fixed by different numbers of initial conditions. So everything really parallels differential equations, and that's good. But it's also potentially confusing. You have to remember whether you're actually dealing with a recursion relation or a differential equation, because the language is all the same. Okay, thanks very much for coming. This will go online. There'll be a link on Vision to this, and stuff will appear there about